Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So as you know, in this module we are trying to understand how the operating system manages the CPU by providing this abstraction of a process, right? So we have just finished the first topic, that is process introduction, and in this topic we talked in detail about like what is a process, how does the operating system implement this abstraction of a process over the CPU. We talked about several aspects, and now we have a good understanding of what is a process. So now we are going to start with a new topic, that is process address space. So basically, we have talked about address spaces in the first module where we're trying to understand how the operating system manages the memory. So we have understood that the address space is an abstraction over the memory, right? So there we talked from the perspective of the memory. Here, basically, we want to understand how the process address space looks like. Basically, with every process, with every running program, there is an associated address space which contains the code and data of that program in the memory. So we want to understand how is the address space of the process organized, how is it laid out in the memory. So here in this topic, through a series of videos, we are going to see what are the different regions in this address space, what does each region is responsible for, right? So by understanding the different regions of the address space, we will have a good understanding of how the memory of the process is organized. So in the first video, I'm going to give a brief introduction about the address space from the perspective of the process. So without further ado, let's get started. So let us start this discussion by recalling the concept of an address space. So in one of the earlier videos, as I said in the first module, we have already understood what is an address space, right? So I'm just going to recall what all we studied in that video. So for example, let's consider a computer system, and this is the physical memory, the DRAM of the computer system. It is a hypothetical computer system. You can see it is just 16 bytes. Okay. So now let us recall what is the address space, what is the address space and why do we have the address space. So basically, as you can see, first of all, as I said, this is the physical memory and it is 16 bytes long. So this, you can see the addresses are starting from 0 and going till 15. Okay. So this set of addresses that you see for this physical memory is called the physical address space. So basically an address space is a collection of addresses. Here the addresses are related to the memory. So an address space in this case is a collection of memory address, and since we are talking about the physical memory, this 16 byte address, basically 16 addresses that you see, this collection of 16 addresses constitutes the physical address space, right? So this was about the physical address space. So now basically let's say there are three different processes in this computer system: process A, B and C. And as you can see, the physical memory contains the data of all of these processes. Okay. So where does the concept of address space, why do we have the concept of address space? Let us understand this. So basically the processes are not allowed to directly access this physical address space. Why this is the case, we will understand later. But the point here is that these processes, process A, B and C, basically all the processes in the computer system, they are forbidden to access this addresses. So now the question then arises that how will the processes access their own data, right? As you can see, all of these processes have their data in the memory, but without referring to the memory addresses, how can a process access its own data, right? So basically what the operating system does is that it in a way basically provides each of these processes with their own address space, and these address spaces are called virtual address space. Basically, let's assume that each of these virtual address spaces contains 4 addresses. So the physical address space contains 16 addresses. We are assuming here that the size of the virtual address space is 4. Each of the processes is provided with 4 addresses, as you can see, 0, 1, 2, 3. Basically, in this computer system, any process can have at max 4 bytes of data, just an assumption. So here in this computer system, every process will have at max 4 bytes. Okay. And in order to access this, they will use these virtual address spaces, basically the addresses in the virtual address space. Now what the operating system basically does is that after forbidding the processes to access this physical address space, it provides the virtual address spaces and maps the data which is present in the physical memory to these virtual addresses. So if you see, let's look at process A. the process A, the light blue color, if you see this address 5, 8, 10, and 13, these are the 4 bytes that are associated with process A. So what the operating system has done is that it has mapped the addresses 0 with 5, 1 with 8, and 2 with 10, and finally 3 with 13. Okay, 3 with 13. So these are the 5, 8, 10, and 13. These are the addresses where the data of process A is present. And now, since the physical address space is forbidden for the process, it what the operating system has done, it has arranged a mechanism so that these virtual addresses are mapped to the physical addresses. And now, in order to access the physical memory, the processes will use these addresses to access the data. So whenever the process A wants to access this data at 5, it will say give me the address at address 0, and then it will be translated to 5, and then this is how the process A will get its data which is present here. Similarly, if it wants the data at address 10, physical address 10, then it will say give me the data at virtual address 2. It will be then translated into 10, and that is how the process will have its basically data. So you can see these are the address spaces. We have one physical address space which is associated with the physical memory, and we have uh, the other type of address space which is called the virtual address space, which is associated with each process. So let's say there are 100 processes in the system, then there will be 100 virtual address spaces, one virtual address space associated with each process. Now the question, let's come back to the original question, that why do we have like this complicated system? Why can't the process directly access these addresses and get the data of their own data? Why do we need to have these separate address spaces, then mapping all of this, then translating while doing a memory access? Why such a complicated mechanism? Basically, there are several flaws. If the flaws, we can say there are several uh, security reasons that exist if the processes are allowed to directly access the physical memory, right? Then what will happen, that any process would be able to address or access the data that belongs to any other process. Let's say process A, let's say there is no concept of virtual address space, and all of the processes can directly access the physical address space. So then what can happen is that process A can say that give me the data at address 3. But if you see this data at address 3, this belongs to process C. And if we allow the processes to directly access the physical addresses, then there will be no data protection. There are several processes in a computer system, and all of them share the physical memory. The data belonging to all of the processes resides in the physical memory, and if we, as you can now see, there will be no data protection mechanism if we directly allow the processes to access the physical address space. So I have discussed the benefits of having this decoupling of the address spaces in great detail in the video where I introduced the concept of address space. But as you can see, one of the most important reasons why do we need these separate address spaces is this concept of isolation. Each process should be only able to access its own data, right? So this is how the operating system, by setting up this different address spaces, is able to ensure this, right? And as we know, the address space is an abstraction that the operating system uses to manage the memory. So having understood the basics of virtual memory, so basically when I say virtual memory, let me talk about virtual memory. So this is the physical memory that we know, right? The DRAM is the physical memory. This is basically the only place where the data is stored. This is the only actual memory, right? When we talk about the virtual address spaces, these are just addresses. There is no real memory when we talk about these. As you can see, these are just addresses, and the only place where the actual data is the physical memory, right? It is a physical memory, it's a physical object. So that is why what we say is that the virtual address spaces creates the concept of virtual memory. Basically, now if you see, each of the processes can only access its own data, right? Via this virtual addresses, you can see process A can only access its own data, same for process B and for process C. So now the virtual address spaces in a way give a subset, or you can say give a limited view of the physical memory to each of the processes. Let me repeat that for you. A virtual address space gives a limited view of the physical memory to each of the processes. And how does this view look like? Basically, this view consists of the data that belongs to that process only. As you can see, process A can view or access only its own data. Same is true for all of the processes, right? So this virtual address spaces creates a view of the view which is a limited subset of the actual physical memory, and this view is how the memory appears to the processes. Now from the perspective of the process A, memory is 4 bytes long and it only has its own data. Similarly, for process B, memory is 4 bytes long and it only has its own data. Same for process C. But in reality, the reality is that memory is 16 bytes long and it has the data of all the processes, right? But having this concept of virtual address space and physical address space, by having this setup, by having this mechanism, the operating system has created an illusion for each process that the memory is private to them, right? And this illusion of private memory is called virtual memory. That is why I have shown this memory as shaded region, right? Basically this is just a view, a subset, a limited view of the original memory. These are the virtual memories. These are not actually memories, these are just view of this memory, and this is the real memory, this is the physical memory. So this was a brief recall of the virtual memory. Now let us see some more points about this virtual memory. Basically, now I want to talk about how the memory looks like from the perspective of the operating system and then from the perspective of the process, right? So basically, as you can see, only the operating system has complete view of the physical memory. The operating system knows that the actual memory, the physical memory, is 16 bytes long, right? And it contains the data of all the processes, and only the operating system knows where is the data for each process. Basically, this all of these mappings are maintained, created and maintained by the operating system. It has the complete access. Only the operating system has the complete access over this physical address space. Now, from the perspective of the normal process, from a perspective of the user process, they don't have access to this complete view, this physical address space, right? So they don't know that in reality how big is the memory, how, like, where the, what are the exact contents of the memory. Like you can see this in the actual picture, the real picture is hidden from the processes because the processes are forbidden to access the physical address space. From the perspective of the individual process, only a limited view of the memory is shown to them. So for process A, it can only see its own virtual, it can only see its own data, right? So this is the view of the memory from its virtual address space. So whatever uh, data to which the virtual address space points to, only that the process can see, and as we know, it can only view its own data. The same is true for process B, the same is true for process C, basically for all the processes in the system. So this is how this setup looks like. So in the computer system, there is a physical memory. It has the data for all the processes. It has the physical address space. The operating system has, only the operating system has complete access over the physical address space. The individual processes do not have access over this. This basically, the operating system forbids them to access this space, and what it does, it provides this virtual address spaces, unique virtual address spaces for all the processes, and now the processes access the memory through this address space, and whatever view of the memory they have is via this address space. So this is how the concept of virtual memory works. So now let's now look, like understand how it is related to the concept of the process. Basically how like the code and data is organized in this address space, right? So now let's understand the structure of the process address space. So we have just studied that with every process in the computer system, there is a unique virtual address space associated with it, right? And this address space, this collection of virtual addresses, gives a view of the actual memory to the process, right? And this address space is also known as process address space. So basically, the point is, with every process, there is a set of addresses which is called the address space, and it is also known as the process address space. And this process address space defines a view of the memory for the process. That is how the memory looks like to that particular process, right? And this address space is where the code and data is organized for that particular process. So now what we are going to do, we are going to look at briefly how the address space is stored for the particular process. Basically, for every process, there is a process control block. We have already talked about this in an earlier video where we studied how do we represent a process. That is, all of the relevant pieces of information are collected into one data structure, which is called the process control block. And this is the example process control block from XV6 operating system. We have already seen this in an earlier video, right? So now let's see how do we store the information related to the process address space. So basically, in each process control block, for every process, basically there is a page table. So we will understand what is a page and why is it called page table later. But basically, what is a page table? A very simple explanation is that it is a table which contains the mappings between the virtual addresses and the physical addresses. So if you see in this particular example, the same example that we have been looking at, for process A, there are four virtual addresses and each of them are mapped to some physical addresses, right? So basically, the collection of these mappings from so basically 0 is mapped to 5, 1 is mapped to 8, 2 is mapped to 10, and 3 is mapped to 13. So if you take all of these mappings, if you collect all of them and put into a table, that is called the page table, right? So we'll understand what is a page, but uh, the point is that the page table is a place, it's a data structure where we store all of the mappings between virtual to physical addresses. And this is how the information related to a process address space is stored for every process. Within the process control block, you store all of the mappings between virtual and physical addresses in a table, which is called the page table. And that is how it is represented in the PCB. Okay, so that is how the address space is stored. So now what we are going to see is that how this address space is organized. Basically, as we already know, this process address space defines how the memory looks like to the process. And the memory contains the code and data for the process. This is a running program which has the instructions, which has the data that has to be manipulated. So let's see how all of this is organized. So basically, there are different sections in this address space. Each of these section has a unique purpose. So as you can see, there are four major sections into which this process address space is divided. The first one is the code section, where all the instructions of the process are stored, the instructions which are going to be executed, and the rest of the different sections are used as a place for storing the data. And there are different types of data that a process, when a program is running, when a process is there are different types of data, and for different types of data we have different sections. So as you can see, there is data section, heap section, stack section. So in brief, let me explain what these sections do. But we'll study all of these sections in great detail in the different videos in this topic. So the very first section is the data. The data section at a high level stores all of your static and global variables, all of the data that is statically generated right before runtime. It's placed in this data section. Then there are certain data that are dynamically allocated. So all of your dynamic memory allocations that happen during the runtime when the process is running, at that time whatever memory is allocated happens on this heap memory. And finally, the stack section, all of this stack section is used as a place where the execution of functions take place. Your program has basically your source code has several functions. It's a collection of functions, and whenever you are executing inside some function. So the execution of a program is like a series of function calls. So this stack section is used for the execution of functions, right? So as you can see, first of all, your address space is divided into different regions. Each region has a specific purpose, and basically the idea is to organize the code and data properly so that the proper execution of the program can take place, right? All of this is properly defined, where the code goes, the instructions, where the data goes, where different type of data, there are different types of data, where each particular data goes, right? All of this is properly defined so that they are properly organized and there is a proper execution of the programs, right? So this was a brief introduction to the process address space. In this video, we basically recalled what is an address space, why do we need an address space. The main purpose of an address space is isolation, so that uh, a particular process only accesses its own data. There are several other benefits of having an address space. I have already talked about that. Then after having a brief recall about address space, we saw how it is actually implemented, how it is stored via the concept of a page table. Basically, it's a collection of the uh, virtual to physical mappings with address mappings. And finally, we saw that the address space basically is divided into different sections, and each of these sections has a dedicated use, right? So this was about a brief introduction about the address space. So in the upcoming videos in this topic, we will look into each of these sections in great detail with examples, and throughout this topic we'll try to have a good understanding of how the memory looks like from the perspective of the process. This is the concept behind process address space. So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.